Okay, welcome back. Now let's look at some applications of CNN in computer vision. So it has been used widely in a number of applications. For example, image classification, object detection and localization, semantic segmentation, where you assigning a label to each pixel in the image, action recognition, whether a person is raising their hands, or pose estimation. You want to estimate the pose of a person. Video classification, scene understanding, tracking, and so on. Pose estimation is written twice, sorry. So before we look at the applications, let's look first at some of the classic, if you want, convolutional neural networks, which constitute a backbone for a number of applications. But before we do that, when you read papers, you look at a certain architecture. They show the architecture and they present numbers there. And just to remind you, we've seen how you find the output after the max pooling, but let's look at the number, for example, of filters. So here you have 32 by 32 by 3. Why would you have here 28 by 28 by 6 and 14 by 14 by 6? So if you have an image, for example, a color image with 3 channels RGBD of resolution 32 by 32, and you apply a convolutional or 6 kernels, 6 convolutional kernels to this input image, and then you these filters are of size 5 by 5, and you do use the convolution with a stride of 1, no padding, 0 padding. So the formula to see what would be the output here is first, because you used 6 filters, so you're going to have 6 channels if you want, and then the 28 you get it by, so this 28 would be the 32 and n plus 2p, which is the padding, so no padding. So minus, should be f here, minus 5. So 32 minus 5 is 27, divided by the stride. So it's 1. Okay, so it's 27 plus 1. So that's 28, and this is the floor operation. The same thing for here. So the output here is the input 28 plus 2 times 0, because no padding, minus, you have 2 filters here. Okay, F should be F here, minus, so 28 minus minus 2, so it is 26 divided by 2, in this case, 2 strides. So 13 plus 1, so that gives you 4, and so on. And then you would see that this is your input, number of filters, so you know how to find for each layer, you know how to find the number of, or the output. And then usually what they do, as we said, is they unroll or flatten your, this one here, the output of the layer, before the last layer, last convolutional layer, they flatten it. So it's, if this is 5 by 5 by 16, so it becomes 400. And then you have a number of fully connected layers of a number which is by design, you get by trial and error to make sure that your performance is maximized or optimized. And then also you can use meta learning to get it. And then you have a softmax at the output. Okay, so now let's look at some of the networks. So first we look at AlexNet. So that was the first large-scale CNN model, which led to the resurgence of deep neural networks in the computer vision area. Computer vision was used mainly in speech and some other areas, but then when AlexNet came, there was a resurgence. There was an interest in the use of deep network for vision, and this architecture won the ImageNet Large-Scale Visual Recognition Challenge, in short ILS VRC, in 2012 by a large margin. So it consists, so you know how to get these numbers. So it consists of a total of 8 parameter layers. So 1, 2, 3, 4, 5, 6, 7, 8, with the 5 initial layers where the 5 first initial layers are convolutional layers. So these 5 are convolutional layers, while the latter 3 layers are fully connected. So you have here fully connected layer. And the output, because it's used with the ImageNet, so the output classifies an input image into one of the 1,000 classes in the ImageNet dataset. And so that's why you have at the output here, 1,000 classes, 1,000 nodes, sorry, fully connected. So these are the convolution layer with the max pooling. And then here you have a dropout, which is applied after the first 2 fully connected layer. So, yeah. So although AlexNet is relatively much smaller compared to the recent state-of-the-art CNN architectures, it is interesting to note that the authors had to split the training between 2 GPUs. That's why you see here 2 GPUs, because a single NVIDIA GTX 580 with 3 gigabyte memory would not or could not hold the complete network, which only had 62 million parameters actually. But then at that time, they had to split with 2 GPUs. Now the VGGne, we talked about it before. So it strictly uses 3 by 3 convolution kernels for all the layers. Each convolutional layer, so you have, this is a VGG16. So you have each convolutional layer. So in black, each convolutional layer has a ReLU, and then followed by a max pooling. And then you have these convolutional layers. After that, you have fully connected layers with a ReLU, and you have a softmax at the end. So using small kernels, 3 by 3 kernels, leads to a relatively less number of parameters. And therefore, you have efficient training and testing. Smaller filter also result in deeper network, which lead to better performance in vision tasks. So when you have a deeper network, so you can, if you have a large data set, labeled data set, you can definitely have a very good performance on the testing set. Another network which is used, as I said, as a backbone is the ResNet. So the ResNet from Microsoft won also the ILS VRC 2015 challenge with a big performance. It is using the top 5% error rate to 3% only, 3.6% from the previous year's winning performance of 6%. 0.7 produced or achieved by GoogleNet. Before we explain or look at the performance of ResNet, let's explain what is a residual network. So residual network is composed of blocks. They call the residual blocks. And if this is the input coming from a previous previous layer or previous residual block, then instead of feeding it just to a convolutional layer followed by a ReLU activation function, and then followed by another ConvNet, for example, and then another ReLU. So this would be your standard plain convolutional layer. So you have this skip connection, or it's also called identity connection, where before you feed or before you apply the ReLU, you take this input and then you add it to the activation or net activation here, and then the result is fed to the ReLU. So here, if this is the transform f of x, so you get here this x plus f of x, okay? So the original input is added to this transformation using a direct connection from the input, which bypasses the transformation layer. So in practice, such architecture enables stable learning of very deep models. And as you can see here, the way you use these residual blocks is you put them one after the other. So this is the plain CNN, where you have a number of CNN layers without any skip connection. So this is your plane. And this is the one, the ResNet with the skip connections, okay? So, and then with the plane model, if you use this one here, the error, training error, is supposed to go in theory like this. But actually in reality, it goes after a number. So when you increase the number of layers, it increases. This has been noticed. And then when you use a ResNet, your training error goes down. So you're able to have a very large number of layers, a very deep network, meaning that because you have a low training error, so your bias is low, and then if you have a large data set, you can reduce your variance. As I mentioned here, or have mentioned here, because the ReLU here, why this is not at least an explanation to show that this operation does not or should not affect the performance, is because the ReLU, the output of the ReLU is either 0 or positive. So if we assume that it is 0, then this would not have any effect. So it's just like you're going to have here X, right? And therefore, just like, but then it has been shown that when the output of the ReLU is positive, this affects the performance. It reduces the training error, but also it reduces, or it helps a lot the performance during testing. So this is with ImageNet, which is a large-scale visual recognition, the ImageNet large-scale visual recognition challenge. So ImageNet has 1,000 classes. where, and then you have, and the data set has 1.2 million training images, 50,000 images are using for validation, and 150 are used for test images. And then if you measure the top 5% error, you see that in 2000 with a shallow network, in 2010, 2011, this was the performance. With the ResNet, just using 8 layers, this was the performance. With VGG 19, with VGG with 19 layers, this is the performance. And then GoogleNet reached 6.7 top 5% error, as we mentioned before. And then with the ResNet in 2015, with just 152 layers, you can, the error was 3.57. So this is a big improvement. So ResNet are used a lot in a number of composite networks, if you want. Or thank you.